In this video, we want to explain the proof of transform densities. We will go over the theoretical proof and illustrate the resulting formula on a real-world example. Our question was how to prove transform densities. The proof in the lecture slides is not easy to understand. Present the proof in an explain video. Every good proof needs a story to explain it. And every good story needs a hero with a randomly generated name. The most easiest way to get a random name is to simply go to Google and type in random name generator. We will here pick the third generated name as the name for our story. Oliver is the first, Socrates is the second, and we will stick to Gordon. As an example, we chose a game of Pong. In this animation, you can see the course of Gordon's game against his opponents. After only a few rounds, Gordon leads with an overwhelming 5-0. To make it more interesting, the last cup will be randomly placed on the table.
The goal of our proof is to derive the equation of the probability density function Py of y from the given probability density Px of x, which is the probability density of how far away the cup is in pink, and the transfer function g of x, which shows how likely it is that Gordon hits a cup at a certain distance in green. So if we combine this, Py of y is able to show us the probability density of how likely it is that Gordon hits the cup given Px of x in blue.
First, we have to check if our transfer function is strictly monotonic, because only strictly monotonic functions are fit to be transfer functions. So for this, we have to know that a function only is monotonic if and only if there is only one x value for every y value, and is strictly monotonic if and only if it is increasing or decreasing steadily. Our probability density of how far away the cup is the integral between 0 and 2 of the probability density function minus 1/2 x to the power of 2 plus 7/6 times x. As already mentioned, to simplify the transformation, for now, we choose g as x equals y. The general idea is simply that we want to substitute x by y. To do this, we need to compute the inverse function of our transfer function g of x. Due to the simple transfer function, in our example we go from g of x equals x to its inverse g of y equals y, which describes the same graph. Therefore, we can now use this to start our proof.
As already shown in the lecture, the derivative of g of y can also be expressed by dx divided by dy. This notation will come in handy while explaining our proof. On this slide you see three different notations for our formula. Don't worry about them now, we will explain them later after the proof. To have a starting point of our proof, we need an assumption. We will here use an assumption which offers us the usage of dx and dy. To go from a probability that x occurs in between the interval a and b to a probability density function, we integrate our function Px of x over the boundaries a to b. To do so, we need the derivative of P of x, which gives us the notation, including dx, we need on the next slide. We know a given interval AB needs to have the same area or integral, here marked in gray, as the corresponding interval alpha and beta on the y-axis, meaning the probability that x is inside the interval AB is the same as the probability of y being inside the interval alpha and beta. In our case, because of our simple transfer function, the boundaries are simply mirrored to the y-axis. So we can say the integral AB possesses the same area as the integral alpha and beta. We now use this knowledge of these integrals being equivalent to prove our goal.
To derive our desired formula, we make use of the general rule for integral substitution, which declares the equivalence of the integral AB
over a function f of x dx to the integral alpha beta over the function f of x of u times dx over du times du, with x of alpha equals a and x of beta equals b. Don't worry if you get confused with this term. We will use this term in a colored manner in the next slide of our proof to make it more clear. As we already know, the areas of the intervals a, b and alpha beta are the same. We now apply the general integral substitution rule. By reducing the term by the intervals and dy, which we are allowed to do since they are the same, results in the term py of y equals px of our inverse transfer function times the derivative of the inverse transfer function, which we wanted to prove. We take dx over dy as an absolute because there cannot be a negative probability.
To reduce the complexity, you can here see the same proof less cluttered. This time we left out the intervals to get a more understandable notation. We now use py of y times dy is the same as px of x times dx, which we showed in the last slides as a starting point for our proof. By simply dividing with dy on both sides and substituting x by the inverse function of g of y, we end up with our originally desired formula. Py of y equals px of the inverse g of y times the derivative of the inverse g of y. From now on, especially for using this formula with numbers, we need to use the inverse function of g of y, which does not affect the values of our equation, because the absolute derivative of g of y is the same as the absolute derivative of its inverse function. To visualize this identity of the slopes, we choose the term g of x equals x to the power of 2, and its inverse function g of y equals the square root of y. The graph on the right depicts the square root of x to see that the absolute values of the slopes regarding to the corresponding axis are the same. Now to go back to our example of Gordon's epic beer pong game. We still want to know how likely it is that Gordon hits the last cup, given our probability density of where the cup actually is placed. To do so, we simply use our derived formula from the last slide. To make this even more clear, we use our probability density function px of x instead of just talking about px of x. As the next step, we insert the inverse transfer function and substitute x by y in our function p of x. And now you finally see why we used this simple transfer function. Because as the graph shows, the slopes of our transfer function is 4 over 4, which is just 1 over the whole range of our probability density p of x. Because our absolute derivative of our inverse transfer function is 1, we multiply the whole probability density px of x with 1. The resulting probability density py of y is therefore just a mirrored px of x. This may seem rather useless, but that's only due to our simple transfer function. We chose this to show the general progress of a density transformation. To not waste your time, we now come to a more realistic transfer function on the next slide.
We now do the exactly same computational steps we took while explaining the easy beer pong example with the complex function e to the power of minus 1/2 x. You still simply substitute every x by the inverse function of g of y in our given probability density p of x. In this case, every x is now substituted by a minus 2 times the natural logarithm of y. The second step we need to do while transforming probability densities is to simply correct the term by the derivative of the inverse transfer function of g of x. In this case, this would be the absolute of minus 2 over y. Here you can see why it is important to use the derivative of the inverse function. This allows us to get a notation solely depending on one variable, here y. On the next slide, you can see our resulting equation on the corresponding densities and transfer function. The orange function is our inverse transfer function. The green area is the probability of where the cups stand and the blue area marks the resulting probability density. What this would mean for Gordon's beer pong game is that Gordon's probability of hitting the cup is high, between approximately 0.35 and 1. If the cup would be outside of the range, he would definitely miss his everything deciding shot. We hope you enjoyed our presentation as much as Gordon enjoyed his beer pong game, and hopefully you now understood the transformation of densities. Thank you for your attention. Peace out, your homies of Group 26.